Hello students. So in this lecture we will be talking about stress evolution in thin films. With argon pressure, what the role this argon pressure has on the evolution of stress in thin films. Now argon gas is used in sputtering. Now, so let us take an example that if we have a 150 nanometer thick sputtered chromium film, and the argon pressure has been varied from 1 to 7.5 millitorr. Then if you could look at the experimental stress evolution, then it would look something like this. So it is based upon the substrate bias that in volts that we provide, and it has varied from say minus 500 volts to 0, and the stress, which is expressed in gigapascal, was found to vary from 2.5 gigapascal. Negative means compressive stress, so it has crossed the 0 mark and it has become tensile. So, at there is a transition zone. So below that it is compressive, and above that it is tensile. So the transition takes place between the nature of the stress as we move from minus 500 volts to 0 substrate bias. Now, so what we observe is that there is a residual stress. In 1 micrometer thick chromium film with negative substrate bias. And there is relaxation of compressive stress, at bias greater than 300 volts. That means this is the transition zone where compressive to tensile stress takes place. So this should be 150, not 1 micrometer. Now, the residual stress that we usually have in films, they have negative effects. So there is a film cracking may take place due to this residual stress. Mainly it occurs due to the tensile stress, and due to compressive stress, the negative effect that we have is delamination. That means the adhesion between the film and the substrate, it weakens. So the film actually gets separated from the substrate, and this occurs due to compressive stress. So two different type of stress have two different type of effects on the film. Now when we are dealing with films which are used in microelectronics, we need to reduce this residual stress, otherwise device performance will go down. Now to reduction of the stress, reduction of stress, the reduction of residual stress in micro dimension. Micro dimension. This is required to enhance the performance of the device, as we have already told you, and also it helps in establishing good interconnections between the different components. Now we need to understand that there are two types of stress apart from compressive and tensile. That is the nature of the stress. There are, in terms of the development of stress, or how the stress gets built up, we can divide the stress into two types. So one is intrinsic, that is due to growth of the film that is taking place, how the film is growing, and where there is an extrinsic stress, which is of course is due to the CT mismatch, coefficient of thermal expansion mismatch between the film and the substrate, or if we're dealing with multi-layers, different layers. So these two are the main causes of stress. Now, as we have taken a 150 nanometer chromium film, so what was observed in the TEM image was columnar microstructures. Columnar growth, that means it was like this type of growth was found. And these regions were between the different columns, they show Fresnel fringes. When we did some focused imaging, so this shows frenal fringes. Now these frenal fringes, they indicate that voids. So frenal fringes they indicated voids. Although they are few atomic layers, but they were voids in the columnar growth. Now to reduce these void, what we have to do is we have to increase the bombardment energy of the ions. Of the ions during the sputtering process, it goes up, then the voids they tend to shrink. Now, however, there is a limitation with higher energy bombardment also. That is, there might be some radiation damage taking place. Due to high energy bombardment of ions. Now this radiation damage again cause vacancies. So it's we need to optimize the energy. Says that even though the method to reduce the voids is causing vacancies, so these vacancies can also be isolated or clustered. So this is also detrimental for device performance or quality of the film. There can be also self-interstitials and there can be Frankel defects also. And there can be trapped organ. So the high energy bombardment is mainly due to the organ ions, so they may also get trapped in the material. Now, if we plot, as we have done a plot with the substrate bias, we plot stress, residual stress with respect to particle bombardment energy or energy of bombardment, and the plot will usually looks like this. Now, it has been also observed that the microstructure uh, or macrostructural growth is in analogy with the stress distribution due to energy bombarding particles. It is told because at around 150 nanometer thick chromium film, we are getting 60 nanometer grain, but as we increased the grain size to 1 micrometer, the grain or the thickness to 1 micrometer, the grain size also increases. So thickness is directly proportional to the grain size, that we can say. So what we can conclude from these results is that there is an intrinsic stress evolution with increasing particle bombardment, and there is a transition from compressive to tensile. Again, you can see that this part is compressive and this part is tensile. So as we had in the case of a substrate bias is in fact is another way of energy bombardment only. So the higher the substrate bias, the higher will be the energy of the incoming ions. The similar nature is being followed here. So there is also a transition from tensile stress to compressive stress, and there is also a maximum limit. So this is the tensile stress max, and this is your compressive stress max. So after reaching the maximum limit, they again tend to go down, or they attain a saturation, if you can say like that also. And because as we have already told you that higher tensile stress may cause film failure, and also compressive stress may also cause film failure. So this is the point where after this the film actually starts to weaken, both in the case of tensile and compressive. And this tensile stress maximum, this or this TS max, give the name as tensile stress max, for physical vapor deposition films. This is actually balancing the sum of elastic strain energy and grain boundary energy. So balancing and creates a balance between, or the reason of its existence is because it creates a balance between the elastic strain energy and grain boundary energy. G and grain boundary energy. Now, there is a relationship by Hoffman who said that this maximum tensile stress is equal to elastic modulus divided by 1 minus Poisson's ratio into delta max by by D, where small d is the grain size and delta max is the relaxation distance. Now, also it has been found that, so this is the relationship by Hoffman, and also it has been found that the adjoining islands, suppose we have a film here, see in the top view, and we have different islands, so it is a natural tendency of the islands will be to get attached and coalesce. So they feel a form of attraction between the different islands, attract each other. This attractive force, so let's put it as attraction of the islands. These attraction, they actually lead to tensile elastic strain. Being developed in the material, and this elastic strain will continue to increase. This continues to increase till there is coalescence. That means two or more grains combine to form one, and they coalesce. So this is, so there are three grains. So now they have come close together. They formed a grain, and they have their grain boundary of their own. Okay, and there is this delta max that we have said is basically the relaxation distance, and there is no direct way to actually estimate this delta max, but physically it means that the distance traveled by the adjoining grains, or the average distance traveled by the adjoining grains to coalesce. So this is what is delta max is all about. So we have got this Hoffman's equation. Let us look at another one. So we can see that this is the equation that is most vital one. So elastic modulus has a role here, Poisson's ratio has a role here. It has the material properties. So it is inversely proportional to D. So you can see that that means the lower is the grain size, the higher will be the maximum tensile strength, and it is directly proportional to delta max, because the further the grains are, the higher is the tensile strain, because the more distance they need to travel to get near to each other and to coalesce.